In our previous video, we had this definition of critical point. A number C in the domain of F is called a critical point of F if either F prime of C is equal to 0 or F prime of C does not exist. The last example we did in the previous video is finding critical points where the derivative is equal to 0. Let's just do a quick example where the derivative does not exist. So if we took f of x was equal to the absolute value of x, our function looks like this here. And the point here is that f prime of 0 is undefined. The derivative does not exist at 0. So 0 is a critical point of f. So it's important to have this in our pocket here that when we think about critical points, we have to think about both when the derivative is equal to 0 or if the derivative is undefined. Most of the time, we'll just be thinking about very nice functions. Everything is nice, the derivative exists, but not always. Okay, so going back to what we've done before with this picture. So we've talked about critical points as being either where the derivative equals 0 or does not exist. And we saw the property that at these local maximum and minimum that they all either had the property derivative 0 or does not exist. So that's not an accident. We have Fermat's theorem here in local extrema. So this tells us that if we have a local min or a max, we are guaranteed that the point that occurs at is a critical point. So if we're trying to find local mins or maxes, the only places that we have to look at are the critical points where the derivative equals 0 or does not exist. And so, but let me point out here, it is worth noting that just because the derivative is 0 doesn't mean that we are guaranteed to have a min or a max. So for example, we thought about f of x was x cubed. So the derivative of this, f prime of x, is 3x squared. And so we see here, f prime of 0 is equal to 0. However, if we draw the graph of what our function looks like here, f of x is equal to x cubed, we see here that 0 is actually not a local min or local max. It's neither. And so just because we have a critical point, doesn't guarantee that we have a local min or a local max. However, in the other direction, if we do have a local min or local max, we are guaranteed that we have a critical point. So let's get back into the main swing of things. We said that in a previous video that we had this theorem. A continuous function on a closed bound interval takes on both a minimum and a maximum value on that interval. And we said we want to think about where those are located. We want to find and identify them. And so here we have this theorem. I think I accidentally pulled it out too early in the first video. Theorem, extreme values on a closed bound interval. If we have a continuous function on a closed bound interval, and if we have a minimum or maximum value, the minimum and maximum values have to occur either at critical points or at the endpoints. And so go back to this original picture at the very start here. We have an absolute maximum. We now see that this is a local maximum as well, and A here is a critical point. Our absolute minimum occurred at an endpoint here. So this tells us that not only in the previous theorem we're guaranteed to have extreme values, but this tells us the only places that we have to look are at the critical points or at the endpoints. So this actually gives us a mechanism for how to find absolute maximum and absolute minimum values of a function. So the only place we have to look are the critical points and the endpoints. So first we identify the critical points. So, f prime of x is equal to 0 and solve that. We have to evaluate the function at the critical points. We have to evaluate the function at the endpoints, and we have to choose our answer. So in the next video, we'll see an example of that.